Welcome back. I'm the Tutor Wizard, Adrian. Please subscribe right here. You'll get notifications for this series and a bunch of other ones on our channel. We're doing the multivariable calculus series. We're in chapter 1, partial derivatives. We're doing section 1.4, which is tangent planes, and this will be roughly the last video in this section. Then we're on to section 1.5, chain rule of functions of more than one variable. Today's lecture, we're going to do differentials on how to approximate for functions of more than one variable. Let's get to it. I'm a wizard, get them both. Alright. Waiting for the cameraman again. Just kidding. What we're doing is, again, just like we did in a function of one variable, first we start off with a linear approximation, then we do these differentiables and then differentials. And then they say, here's a function and approximate this value using a linear approximation or differentials. Pick your poison. This time it's the same. We just have a function of two variables. We gave the definition in the last video of the linear approximation of a function of two variables. That turns out to be the tangent plane this time to the surface at that point. That's this guy. What we now want to do is, I didn't draw the fancy picture, but if you look in the book, essentially in the one dimension we have the tangent line and the curve, and then near the a value, our function is close to the approximation of the tangent line. The same thing here. So delta z, the true change in z, our function's values, is at between the points x, y, and a, b, are f of x, y minus f of a, b. That's the change in the z coordinates. That's approximately equal to, we're saying this is the linear approximation, delta z is approximately equal to the linear approximation of the z near that point AB. Putting that in there, therefore, we notice that cleverly the f of AB cancels with f of AB. Then we call these guys differentials, dx and dy. We have two of them this time, and we're going to say that near the point AB, but not necessarily exactly equal to AB, delta z is approximately equal to the first derivative of f with respect, partial derivative with respect to x, times the differential dx, plus the partial derivative of f with respect to y at AB times dy, and that is what we're going to define, long story short, as the differential dz. In one dimension, remember we had y equals f of x is what I'm saying, and then we had a differential dy, which is defined to be f prime of a dx near a. Now we have just two of them, and we're calling dz equal to the partial of f with respect to x dx plus the partial of f with respect to y dy. Let's do an example of how we use differentials. All right, example. We have a function z is 5 over x squared plus y squared. What they want us to do is approximate the change in z when we change from the point -1, 2 to this point -0.93 to 1.94. Now you can see, instead of just having a single variable x and where we had a differential dx and we've changed that slightly, we're now changing the x direction slightly, and we had a positive. So if we look at this, how did we go from -1, I'm asking myself, to go to -0.93? What do I add to -1 to get this value? -1 plus delta x, or what we call dx, has to equal -0.93. You can actually set it up in an equation. What's that going to say? Dx is -0.93 plus 1, which is 0.07. That's technically how I solve that. But now I have the differential dx and I have the differential dy. Once I have those, turn your phone off so that they don't interrupt us. Billy Baran, he's teaching another one of the differential equation classes for the University of Alberta during COVID. So he's asking me questions about, well, how's your class going? I'm doing videos, just hang on a second, I gotta phone him back, but we're coordinating. Where was I? We'll edit it. I was doing this, which I don't need anymore. Are these toxic? I don't know. Let's hope not. We want to change a small change from this point to this point. We figured out that we would have a differential dx. We increased the dx slightly, and then we've decreased y slightly. And then I didn't do it. Go back to one of the previous videos in section 1.3 and do how to calculate partial derivatives. There they are. I've calculated the two partial derivatives ahead of time of this function. Awfully similar. I like the symmetry and what ends up happening. At those points now, f of x1, 2, I get, it took me more than one try to calculate these, math is hard, It's 2/5. I forgot the square the first time. 2/5 is this, or 0.4 if you like decimals. And negative 20 over 25. Also, these guys, I don't like that. Negative 0.06 is going to be equal to negative 3 over 50. And 0.07 is 7 over 100. I can't have that one. They're relative to prime. So I like the decimal, the fraction avatars. Everyone else like the decimal avatar because their calculator tells it what it is. Now let's put that together and find out what this differential is and approximate this. What that says is the change in z. You're like, all I want is, how do I put this together? Yes, is approximately equal to dz, the differential dz. But now that has two terms in it instead of one. For a function of one variable, dy is f prime of a dx. Now I have dz is equal to fx at ab, which our point is negative 1, 2, times who? dx. Plus fy of negative 1, 2 times dy. And now we have all those pieces. dy is negative 3 over 50, a number. Yes! Not today, Satan. dx is a number, independent variable. And these two guys now, when I evaluate them, number, no more mumbo jumbo. This is equal to, this guy is 2/5. Oh, there's some kind of magic happening on the board there. Times dx. Who's dx? If I'm not doing this wrong, that guy. And then plus fxy is who? This guy. Negative 4 over 5. Oh, a negative. Don't worry, I got another one. Actually, subtraction might have been better. Times 3 over 50. Which is equal to what? No. 14 over 500 plus, what do I have? 12 over 250. Oh, I have to get a common denominator. This one's missing what? So we're going to get 24 plus 14 is 38 over 500. Just a second. How many times does it go into 380? 0 times. What do I get? 0 again, and I bring it down. How many times does 500 go into 33,800? I don't know. This one, 7. So what do I get? 3,500. What do I get? 300, and then I bring a 0 down. How many times does it go into 3,000? Oh, 6. I don't need a calculator. This says delta z is approximately equal to dz, which is equal to 0.076. Please subscribe right here and hit the notification bell. You'll get notifications for this series and many others. I'm the Tutor Wizard Adrian. See you next time.